chapter 20, activity 3. And we start off with the Wittig olefination. So even though it's a W, it's pronounced with a V sound. So it's a Wittig olefination reaction, which utilizes an aldehyde or ketone and what's called a phosphonamide. And I don't know if how well it was covered in the video. So just to go over the ylide quickly, the ylide is prepared from the alkyl halide. So for example, this particular ylide, you could start with a sort of generic alkyl halide, and then you would treat this with something called triphenyl phosphine. And just remember that phosphorus is kind of like nitrogen. It's right under nitrogen on the periodic table. So it has a lone pair, and it can act as a nucleophile like nitrogen. So triphenyl phosphine is pretty nucleophilic and can do an SN2 reaction to kick out a bromide. And then we have, you draw them all out, 3 phenyl groups attached to the phosphorus and the kicked out bromide. And then just like nitrogen with 4 bonds has a positive charge, the phosphorus with 4 bonds has a positive charge. So then that actually makes the hydrogens next door more acidic. So we can use butyl lithium. So sometimes that's written just BULI, but that's basically, think of it as kind of like a Grignard reagent. The 4 carbons, the last carbon attached to the lithium. It's a strong base, like a Grignard reagent, and it can deprotonate that proton and form what's called the ylide. And so I could, with charges drawn in, that would be a negative next to a positive charge. And then this is just one resonance contributor. Sometimes people also draw the other resonance contributor, which involves electron sharing on that carbon. And so that's when you will see the double bond to the phosphorus. And in that case, we don't draw charges. And so these are contributors, and you could see it either way, but this is known as the ylide or the phosphonium ylide. And it's the reagent for the Wittig olefination reaction. And so it's important to just recognize that that came from an alkyl halide through a 2-step process of treatment with triphenyl phosphine followed by butyl lithium. Okay, so when we mix an ylide with an aldehyde or ketone, we'll end up getting an alkene. So we're forming a new carbon-carbon double bond, which is pretty unique. Normally we form carbon-carbon single bonds, but form a double bond is pretty unique to this reaction. The byproduct is triphenyl phosphine oxide, which is usually a solid, not very soluble, so people can just filter it off. So it's a byproduct. Okay, so for the mechanism of the reaction, we can draw a 2+2 reaction. So we can basically show the electrons shifting, form the 2 new sigma bonds simultaneously from the 2 pi bonds. That forms this 4-membered ring, which is in high energy intermediate, which will immediately decompose to what's called a retro 2+2, and forming now triphenyl phosphine oxide and our new carbon-carbon double bond. And this is an error. Notice that says CO3 methyl, but that doesn't make sense. Okay. So looking at the reaction, whenever you see an alkene and thinking about synthetically making it through a Wittig reaction, you can disconnect it 2 different ways. So one side will be the carbonyl, and the other side will be the ylide. So this is showing you 2 different ways of either the carbonyl is the component sort of on the left or the component on the right, and the other one contains the carbons attached to the triphenylphosphine. So this is practice showing identifying 2 different components that could have made these alkenes. Right? So we're thinking about making this carbon-carbon double bond. So we can either put the carbonyl on the left or the right. Let's say we put it on the left, that would make acetone. And then in that case, we would attach the other 2, the others to a triphenylphosphine. Right? Or you could have the opposite. So we could do the ylide is on the left, and carbonyl is on the right. So either way. Moving on to the next one, we can get this one. We either put the carbonyl on the left, do that, then that would make hexanone, and we could put the ylide on the right, triphenyl. Make sure not to lose any carbons. The other option is to have the ylide be on the left, and then the carbonyl, which in this case is an aldehyde. So moving down here, the same process, just extra practice for you to think about making it 2 different ways. One way or another way. And I think people just generally use the double bond form of the ylide just because it's easier than drawing out the lone pair charges. All right, so next one. One component H. And then just always recognizing that the ylide came from an alkyl halide. Okay, so moving on to stereochemistry of the Wittig reaction. So when you have attached here is a just a regular alkyl group, then typically the V isomer is favored. If you have attached here an electron withdrawing group, then the E isomer is favored. Okay, so it's basically, this we call a stabilized ylide, because if you think about the other resonance contributor, it's easier to see why we call it stabilized ylide when you draw out the other resonance contributor. So when you see the one with the negative charge here, it's going to be stabilized when it's next to an electron withdrawing. It's able to pull out some of that electron density. And in this case, the reaction is reversible and eventually forms the more stable E isomer. And if you imagine this case, right? So this is the alternate structure here is not stabilized. The negative charge is just next to an alkyl group. And alkyl groups, as you know, are weakly electron donating. So they don't stabilize the negative charge at all. So this reaction is the kinetically favored process, and we end up getting the Z isomer. Okay, so predicting some products here. We have sort of zipping this together. We can sort of trace out the carbon backbone for the carbonyl component, add in the double bond, and then we have this methyl group here, and where is it going to go, right? Is it going to go sort of this direction or that direction? Those would make two different products. And so in order to get the Z isomer, we would actually put it on the same side of the larger isopropyl. So because this is an unstabilized ylide, we end up getting the Z isomer. Over here, we could, this one is not going to end up mattering because there's two identical methyl groups attached to the same carbon. So it doesn't really matter if you put the ester CO2 on one side or the other. Makes no difference. No stereochemistry there. Over here, the phenyl group is actually considered to be, even though it's not really electron drawing, it's considered to be a stabilized ylide. And that's because the lone pair is resonance stabilized through the ring. So if we draw the other contributor, you can see how the lone pair here is stabilized in the ring. This is actually considered a stabilized ylide. This will give the the E isomer. So when we draw that, we're just going to be careful to attempt to draw that as an E. So we'll go ahead and add in. Just to make sure it's clear, we're trying to draw E isomer. And then again, this ylide is unstabilized. This is just a regular alkyl group. So it'll be, if stereochemistry is evident, it will make the Z isomer. So we just kind of start with one of the components here. And then I usually just draw in the double bond and then think about, okay, am I going to make this Z or E? I want to make it Z. So I'm going to go ahead and come off of this side. And you can always do a little double check on the number of carbons, make sure that you did not add any extra or use any non-active. So if you count up all the carbons here, it should be the number of carbons. Moving on, we're going to start talking about the Baeyer-Villiger oxidation. The Baeyer-Villiger oxidation uses a peroxy acid. So you can think of RCO3H as sort of equivalent to MCPBA. When you see those are like interchangeable ways of saying the same thing. And interestingly, the Baeyer-Villiger oxidation is able to insert an oxygen in between the carbon-carbon bond. Right? And if it's an unsymmetrical ketone, then we need to know where is the oxygen going to insert, right? On which side if these two are not the same group. So it follows this migratory pattern of protons migrate the fastest, followed by tertiary carbon, secondary and phenyl are about the same rate, and primary and then methyl. Okay, so secondary versus phenyl would end up giving you a question. They migrated about the same. So let's look at some examples here. And by the way, maybe I don't know if we went over the mechanism, but it might be kind of cool to look at the mechanism of the Baeyer-Villiger oxidation if it wasn't, if it hadn't been gone over. Maybe we can do that. Get to the activity. Okay, so whenever you have an unsymmetrical case, right, then we have to think, okay, which one is going to migrate faster? So hydrogen atom or tertiary alkyl group, right? And then we know that the hydrogen atom migrates faster. So the short way is whenever you have an aldehyde, you'll always get a carboxylic acid because the hydrogen migrates so fast. Right? So it will insert between this carbon-hydrogen bond faster than any other carbon-carbon bond. So that ends up giving us a carboxylic acid. This is kind of not a very useful reaction necessarily because we know we can just oxidize aldehydes to carboxylic acid. So for example, we could use sodium bichromate to oxidize the aldehyde to a carboxylic acid. So we have other ways of doing this reaction, essentially, just a regular oxidation. So it's really a more useful reaction with ketones than with aldehydes. Okay, so, and then just note how sometimes he writes MCPBA, sometimes he writes sort of other peroxybenzoic acids, like a methyl peroxybenzoic acid. Remember that those are just kind of equivalent. This is the most common peroxybenzoic acid used, but it's not the in this particular case, we have a symmetry. Right? So this is symmetrical. So it doesn't really matter which carbon-carbon bond you insert the octane in. So we're just going to, but we are going to expand the ring, right? So we had a 6-membered ring, and now we're going to have a 7. Okay, and here, noticing that this is an aldehyde, right? Whenever we have an aldehyde, we end up just getting the carboxylic acid. So in this case, now we have a tertiary carbon versus a primary carbon, sorry, secondary. And so we're going to end up inserting this because of the migratory pattern. Tertiary is faster than secondary. And so we will end up with a 6-membered ring because we had a 5-membered ring before. Whenever you start with a cyclic ketone, you end up with a cyclic ester, also known as a lactone, where the ring is expanded. One size larger ring. And then in terms of what migrates faster, phenyl or methyl, right? Phenyl is a little bit faster than methyl. And so we're going to insert between that carbon-carbon bond with the phenyl. So we end up with ester. So you can think about, like, this is a pretty cool reaction, right? Because it would be hard to think of any other way to do that besides the irregular oxidation. But we have other ways to convert aldehydes to carboxylic acids. Okay, so talking a little bit about sulfur-based nucleophiles and their reaction with aldehydes or ketones. So just like making an acetal with an alcohol, we can make what's called a thioacetal with a thiol. So remember that sulfur is under oxygen on the periodic table, so it reacts very similarly to oxygen. Not exactly the same, but there are some similarities. So the most important application of making a thioacetal is using radium nickel. So it's common to essentially reduce the carbonyl completely down to a CH2 group through forming a cyclic thioacetal and then followed by treatment with radium nickel, which cleaves the carbon-sulfur bonds and replaces the bonds. So radium nickel is a nickel alloy, and it's been impregnated with acids. There's acid in there, and the acid is providing the protons, and the nickel is providing the electrons to do this reaction. Okay, so one way you could see that, an application of that is in synthesis. Right? So we can do a Friedel-Crafts acylation reaction. Okay, and then this is a meta director. So we can introduce the nitro-group meta to that group. And then recall, what if we had wanted to reduce this carbonyl, right? And we also wanted to reduce the nitro. So if we had wanted to reduce both, we could use zinc or zinc mercury in HCl, and that would reduce both of those. But what if we only wanted to reduce the carbonyl? Remember that the zinc reduction will reduce both if they're present, so it's not selective. But this is selective, right? You could selectively use this to reduce a carbonyl in the presence of a nitro group. So you would the dithiol would form the cyclic thioacetal, and just like an acetal formation. And then rhenium nickel would reduce those two bonds completely. So you would end up reducing the carbonyl entirely without touching the nitro group. And so that's very useful application of that reaction. Something we couldn't do with the Clemmensen reaction, which is zinc acid. Okay, so here are some more reactions to practice with. So far we haven't talked about the conditions of potassium, cyanide, and acid. And sometimes acid is just written as hydrogen cyanide. Because of course acid and cyanide will somewhat react to form HCN. So either way, any kind of acid, including HCN, you can use for this reaction. This reaction is it forms cyanohydrin. They're called cyanohydrin formation. Sometimes the names, you don't have to memorize the names, but they can be useful for remembering the reactions. Sometimes names are useful. So we just draw in the product there. And then noticing that this is a cyanohydrin over here, right? That could have come from a ketone and cyanide. So, and reduce this down to the ketone starting material. Looks like this is an 8-membered ring. Careful to attempt to draw an 8-membered ring. And this is the rhenium nickel reduction of the cyclic thioacetal. Remember that just completely removes that carbonyl all the way down to a CH2, which in this case would make methyl butane. And in this case, we have the reduction of a carbonyl, right, with the rhenium nickel, and the carbonyl really could be anywhere. There's lots of potential answers. So you just put the carbonyl really anywhere. It could be part of the ring. It could be an aldehyde on this carbon at the end. It doesn't really matter. I'm going to put it over there. Okay. And the next reaction is has a name. So this one is the Wolff-Kishner reduction. So like I said, sometimes names can help us remember what's happening. This is another way to essentially reduce the carbonyl all the way down to a CH. The advantage here is the fact that we're using basic conditions. Notice the KOH. Whereas the rhenium nickel is an acidic condition. Remember I told you the nickel alloys has acid in it. And then the zinc mercury amalgam with HCl also is an acidic condition. So those are 3 different ways to essentially remove a carbonyl. And this is the only way that utilizes basic conditions and not acidic conditions. So if you were really trying to be careful and not use any acid on your compound, then you want to choose the Wolff-Kishner reduction. And then again, this is going to be removal of a carbonyl. And again, there's lots of potential answers here. You could put the carbonyl anywhere. So you decide where you want to put it. Here, there. Again, lots. Hard to know exactly where the carbonyl was. That was. Okay, the next reaction is a Baeyer-Villiger oxidation. In fact, the next two are Baeyer-Villiger oxidations. And so they are using peroxybenzoic acids, and we just have to look and see, okay, where is the oxygen going to insert? So in this case, it's going to insert here, and so we just have to carefully draw that. When it's a ring like this, you need to draw the next size bigger ring. So 6 becomes a 7-membered ring. So we're going to attempt to draw 7-membered ring. Sometimes these rings can be tricky to draw. And in this case, it is not, carbonyl is not part of a ring. It's a little bit easier. So then thinking about the starting material over here, reaction, you just need, if this is a 6-membered ring, and came from a 5-membered ring. So we're going to go ahead and draw that 5-membered ring, methylene. And then if we had carboxylic acid, that came from a aldehyde. So remember, methyl lithium is just like a Grignard reagent. So when you see methyl lithium, just think of it as exactly like a Grignard reagent. You know it would attack the carbonyl carbon using alcohol. And then clearly we got this methyl from the carbonyl. It's just cyclopentanone. Okay, so this is the Clemmensen reduction. And it reduces carbonyls all the way down to methylene. All the way down to that CH2 group. The only position to put the carbonyl, this particular one, is here. There's only one answer possible for that one. This is just the review reaction of a Friedel-Crafts acylation reaction. You know that the methoxy group will direct that era. Okay, and then this was introduced via the Friedel-Crafts reaction. We just have to remove it to generate the starting material. Moving on to synthesis, provide a synthetic strategy. There's actually several you could do for this one. And I'll offer a different alternative than the key does, just to show you that you can do different things. So I think the key brominated the ring and then formed a new carbon-carbon bond via a Grignard with an epoxide. So that's one option. Another option would be actually to just introduce a methyl group through a Friedel-Crafts alkylation reaction. And then once you have that benzoic carbon, now you can react it. One of the things you can do is add a bromine through NBS with light or heat. So that will introduce a bromine on the benzoic carbon. Now we're at benzyl bromide, as it's called. And now we can convert this to a carboxylic acid through either forming a Grignard and reacting it with CO2, potentially, or you could use sodium cyanide and an acidic hydrolysis. So, for example, there's a couple of different ways you could do this. You could use Grignard with CO2 and acidic workup, or you could treat this with sodium cyanide and do acidic hydrolysis on the nitrile to form the carboxylic acid. A couple of different options there. Notice that this is one carbon homologation. So ended up adding the carbon here. So we want to make sure that we use one of the reactions that add the carbon. So that is your alternative pathway to the key, which I believe thought about adding a bromine instead of a methyl. And then using a Grignard reaction. He utilized an epoxide in order to get a functional group, an additional carbon away from the ring. And oxidation. At this point, you have the right number of carbons. All you have to do is do a sodium dichromate oxidation from the primary alcohol to the carboxylic acid. So multiple options here.
I'm a bit confused with the NaCN.
Sorry, can you repeat that, Victoria? I couldn't hear before.
Oh, sorry. The NaCN with the acid and heat, I'm a little bit confused. Well, what reaction is that, or?
Okay, so that one is, oh, you know what? I just realized that that is from chapter 21. So no wonder you this wasn't on me. The reason why it was fresh in my brain is because I just made the tomorrow's activity video yesterday. So I'm a little ahead of you guys
Okay.
in terms of what you've seen. So yeah, so sorry, these are both.
Oh, both of them. Okay, yeah, because
These are both chapter 21 reactions.
Right. Okay.
So yeah, it's like, I think you guys have seen it just because I already made the video on it, in my brain, but I just realized that that's not the case. So I'm not surprised that he used this one because this one utilizes reactions that you guys have seen. Yeah, so we'll learn how to do these in the next activity. So tomorrow. Okay. Good question. So now from the alkene to an alkyne, right? We can do that and then we can just alkylate the alkyne. So there's a multi-step sequence to convert an alkene to an alkyne. First we brominate the alkene, and then we treat that with excess sodium amide and water. That does a double elimination. That ends up giving us the alkyne, and then from the alkyne, we can do an alkylation. Just want to make sure to add the right number of carbons in that alkyl. More review here, it looks like, and some new reactions at the end. Okay, so we want to do a Markovnikov hydrohalogenation. We want to do an elimination to get the Zaitsev product. We want a small base for this. In this case, we want to do another hydrohalogenation, so add H BR across the double bond. Now we want it to, the bromine to go to the less substituted carbons and add some peroxides. This is a Grignard reaction, introducing new carbons. So we'll do magnesium into aldehyde. And then this is an oxidation, secondary alcohol ketone with PCC. To make this, convert this carbonyl to an alkene, we need to do the Wittig olefination. So we'll be adding in these carbons as part of ylide. Just draw that particular ylide. Wittig reaction. And then the last step is the oxidation, so MCPVA or bromine water followed by sodium hydroxide. Okay. Now we're going to be proposing a mechanism, right? So, and then probably if we want to draw a mechanism, we should go ahead and throw in all those lone pairs. And hydride is being used. Hydride is a strong base. So that's typically what it does. It doesn't, if it was sodium borohydride or lithium aluminum hydride, it would reduce the carbonyl. But hydride not attached to boron or aluminum is more basic than nuclear. So it will actually the most acidic proton here, which is the thiol proton, which has a pK of about 10. It's actually pretty acidic. Generate the negatively charged sulfur atom here. And then now this is a pretty good nucleophile that could do a nucleophilic attack. And the reason why this can reach around here and do this attack is because think about the ring size, right? So 1, 2, 3, 4, 5, 6, or if you count this way, 1, 2, 5. Those are both reasonable transition states in terms of ring size. So to be careful here, we can kind of draw it like this. Have this bicyclic ring intermediate, which can do lots of leaving group. Well, oops, what did I do? Oh, I'm going there. Now we're very close to the product here, and we just need to protonate this, right? And that will probably happen in the workup. Protonation as part of acidic workup. New reactions. So this is a bit weird in terms, I think that it's so funny because he almost never uses 9-BBN properly, which is when you would start with an alkyne. He always writes borane. You should use 9-BBN. And now when you don't need 9-BBN, he has it. So it's a bit strange. I'm just going to go ahead and change this to borane.THF. So 9-BBN is more for triple bonds. It's bulky and it prevents side reactions. So with an alkene, normally you would just CH3. Anyway, The idea is that this reaction is a hydration and it's anti-Markov. So we would end up with the OH here, right, and the hydrogen here. And then the stereochemistry, it doesn't say necessarily to consider stereochemistry, but this one has a very specific stereochemistry, so we'll go ahead and draw it in. So remember that the hydrogen here and the OH get added on the same side. So then the methyl gets pushed down. So that's stereochemistry. And here, this is a epoxidation condition, right? So bromine in water followed by sodium hydroxide will form the epoxide. And then because these two groups are on the same side, then we typically can just draw those two groups, both on a dash or both on a wedge. So I'm just going to draw them both on a wedge. So here, this is an alkoxymercuration demercuration. Remember that the alcohol will end up with a more substituted carbon. We'll end up putting that here. Ethyl group. No stereocenter formed there, so we need to worry about stereochemistry. And then now this is a conjugated diene reacting with HBr at 40 degrees Celsius. So this is elevated temperature. You're going to get the thermodynamic product here. The hydrogen will go on one of the terminal carbons, right? Then the alkene will be most stable when it's most substituted, so we will go ahead and put that here. One of the carbons gets a bromine, the other one gets a hydrogen. Draw in if you want or not. Technically, there is stereochemistry here, but I'm not going to draw it in for this reaction because usually we don't. So this is the chiral center, will be a mixture of enantiomers. In addition, this is the alkene. It also gets the alkene. So there's a variety of products there when considering stereochemistry. Usually just ignore.
For the Br2H2O, that's the halohydrin, right?
Yeah, this is the halohydrin followed by sodium hydroxide. So then this does the Williamson ether kind of thing to make the epoxide. So just recognize this entire thing as being like a epoxide equivalent to MC.
Oh, okay, it's equivalent. Okay. Oh, I'm forgetting so much though.
That's okay. That's why these good review reactions are in here, right? So this is, we'll write that in, equivalent to. That's why we review, right? Sometimes you can just.
Okay.
So did Dr. Wynn go over, Victoria, did he go over the Baeyer-Villiger oxidation mechanism?
I'm going to be honest, I haven't seen the rest of the video, but I did read it, and the mechanism was in the book.
Yeah, okay. I'll just leave it off for now then, and I think it's on the practice exam. I'm sure people will ask me eventually.
Yeah, I saw it, and I was a little confused. I know that, you know, it migrates one of the groups, but I don't know why, like, confusing. So, I mean, if you want to go over it, that would be helpful.
Okay, sounds good, I will. So if we have let's like do a specific example, right? So we can do, how about let's do an aldehyde. Drawing everything out. So we have an aldehyde and it's being reacted with MCPA. And I think in the book you probably see R's, like R1 and R2. This is just a specific example. So I'm going to draw out some, basically I'm just going to use MCPBA, but it could be any R group before the peroxybenzoic acid. But we'll just use the most common, which is MCPBA. course, there's the lone pairs on the chlorine. Those don't really matter, but okay. So one of the things to remember here is that the lone pair here is partially tied up with the oxygen in resonance. So this is actually the nucleophilic oxygen, and that's not close to the other oxygen. So we can actually show a nucleophilic. So what that looks like. I'm going to draw in a little bit. Lone pairs usually do with mechanisms. See that very well. And then the charges as well. So this hydrogen actually is really in close proximity to this lone pair because it's part of a 5-member green. So it's basically hydrogen bonding already to this intramolecularly. So it's not a big jump then to think maybe that the proton could just transfer because it's already sort of hydrogen bonding to this in a stable 5-member ring. So we'll go ahead and do that proton transfer. Those lone pairs. Okay, now we're here. So we've done the nucleophilic attack and the proton transfer. And then if I can point something out, right? This is essentially now a really great reading because as soon as these electrons leave, right, you could think of them doing something like that, and then they would form a carbonyl here and an OH group there. So it's just a carboxylic acid. Once that leaves, you can kind of imagine, right? We've just essentially generated the carbonyl and the OH, carboxylic acid. This is a great leaving group, right? But if we just make that leave, that would leave this oxygen with only 6 electrons around it, right? So it would be pretty electron deficient. And there's a driving force to use these electrons to regenerate a double bond. But in order to regenerate a double bond, something has to leave this carbon because it would have too many electrons. We can actually do a hydride shift, right? Basically a shift or a rearrangement. And that will allow this double bond to form, get rid of a set of electrons by shifting it over, make it so that this oxygen now going to have 8 electrons around it, and this is a big leaving group. It's a lot of arrows, but if you kind of understand like why they're happening, it might be a little bit easier. So then drawing sort of what's happening here, right? We've got regenerated the double bond here. This hydrogen shifted over to the oxygen, so this becomes an OH group. And then this other group is just a leaving group. So this became the carbonyl and double bond here, and then this became a single bond OH. This is a byproduct, just like the same byproduct you would get when you use NCT oxide with an alkene. Byproduct, you're only transferring the one oxygen. So the hardest part is seeing this shift, and it's which group migrates, right? And so it's remembering that migratory aptitude of the hydrogen migrates fastest. So that's why we chose to shift the hydride and not the methyl. Right? But let's say it was two different groups. Then after that, it would be a tertiary carbon, secondary and phenyl at the same rate, right? Then primary and methyl. This is really an easy one because we have either the hydrogen migrates, so hydride migrates, or the methide. And they're on opposite ends of the spectrum, how fast they migrate. This is going to migrate much faster than this. So does that help a little bit?
Yes, it does.
Okay.
I think there's just a lot going on, you know.
Yeah, there
But,
is.
So okay, so if they were like different, like tertiary and secondary, you just determine like you look at the carbon at the end or like right there, say like
Yeah. Yeah, so
okay.
just it could be like very generically, right? It could be these are two groups, right? You could think of one of these is going to be X or R1, one of these is going to be Y, right? And so these are two groups up here, so the X and the Y. They don't have to be methyl and hydrogen. Could be anything. So, for example, if we had started with, instead of that, if we had started with, let's say, phenyl, right, and the tertiary carbon, then once we got to that position, we would have, we got to that intermediate, we would have phenyl or that tertiary carbon, thinking about, okay, what migrates, etc. So then it's okay, the tertiary carbon migrates faster than phenyl. We would make sure to migrate the tertiary carbon here. Does that make sense?
Yeah.
You could basically shift the methyl over, you could shift the isopropyl group over. You have to look at this priority to figure out what gets shifted. So it's the same idea. Shift that over.
Okay, so I guess this
So
sounds kind of, I just want to make sure. So you're where the 3 is at, you're looking at that carbon, right? That tertiary.
yeah, yep, this carbon.
Okay. That makes sense. Thank you.
You're welcome. So this is failure oxidation. Okay. Do you have any other questions for me now?
The Wittig or that reaction, I'm still a little bit confused. In the textbook, it was saying something about when you prepare it, that since you're using the SN2, primary will be faster than secondary. Does that really matter in this case? Or like, and it didn't talk about stereoselectivity, so it was a little different, I feel,
Yeah.
but
Okay. Yeah, I'm just
know,
kind of going off of what he has in his activity and how much he intended for you to know about that. But you were right. So your first question about the making of the Wittig reagent, right?
yeah.
And how it's because we're relying on an SN2 reaction, it is much better for this to be a primary carbon or methyl, right, than secondary. And so that is true. So when you come over here and you look at some of these choices, we didn't talk about this at the time, but you could potentially rank this in terms of what is the better option, right? Based on the illid. So, for example, here it's attached to a primary carbon, versus over here the carbon attached to the phosphorus is secondary. So this is actually a better choice. terms of ease of preparation of the illid, because it comes from a less sterically hindered reactant. So that's the idea, but does it really matter? And I would say the answer is no, because even a secondary carbon is kind of okay in this case, because the triphenylphosphine is a super strong nucleophile and it's not basic. So there's no competition between substitution and elimination where you'd have to worry about a secondary carbon doing an elimination. That makes sense. So it's going to do the substitution.
Okay,
But
that does make sense.
yeah, I think it's not going to do, like with the secondary alkyl peli, it's not going to do.
I'm not really sure why the book emphasizes
I know
that so
the book is a little bit weird about pointing it
I was
out.
like,
It doesn't
yeah.
really matter.
Okay,
But
it's
the book's
crazy.
yeah, the book's point is basically like, okay, just take a look at these two carbons. Whatever is less substituted is easier to form the illid. You'll get a higher yield, basically.
Because on the practice quiz, you know, the last question with the IR, it was like secondary, the bromine was on the secondary or something like that. Alkyl halides. I was like, wait, why? You know, but
Yeah,
so it
it's
doesn't really
fine.
matter.
It's fine. Yeah.
Okay.
It's really fine because, again, I do think it makes sense for him to kind of drop that because, like I said, there's nothing else that can really happen with the reaction. That's a big concern. Triphenylphosphine is not going to act as a base and do an elimination. So it doesn't really matter. Primary and secondary, you can still do in essence